All right, Assalamu alaikum, friends. So today is going to be our seventh lecture in the condensed matter physics class. Uh, we are starting our investigation of how do we probe the internal structure of crystals. How do we know that atoms are in a particular space group? How do we know the geometrical arrangement of atoms inside the unit cell? And by the way, the unit cell is all that you need to know besides the overall size of the crystal. But once you know the contents, the ingredients of the unit cell, you know everything about the crystal. So there has to be some mechanism of probing the internal structure of the crystal. And we've already discussed in the previous lecture about directions and planes. So we'll take this concept a bit further today. And so let's get started. So let me share my screen. So does anyone have any questions so far? So today we're going to start our seventh lecture, and we're going to look at a really interesting concept, somewhat of an abstract concept, but of immense use. And this is the concept of the reciprocal lattice. Okay, so let's start off by invoking the following idea. Suppose I have a plane inside a crystal, and we index planes by the Miller indices HKL and put them in parentheses. Now, one idea is to draw the plane itself and put the indices next to it. So this will identify the plane. But another approach is what I would call the blind man's stick approach. And this means that instead of specifying the plane or drawing the plane itself, we could talk about the direction of the plane. And the direction of this plane can be specified by drawing a vector that is normal. I think I need to mute Heather. Uh, so can you please mute your microphones if you haven't already? Okay, so now we have a direction. Let's call that direction UVW. And we put this direction inside square brackets because we always put directions inside square brackets. Now, what I would like to promulgate or propose is that if we have a vector that is normal to the plane, that vector is good enough as far as specifying the orientation of the plane. So we could either draw the plane itself and identify its Miller indices, or we could draw a normal to the plane. You change the orientation of the plane, the normal changes. So here is one plane, here is another plane. So changing the orientation changes the normal vector that I've drawn. Now, what are the directional indices of this normal vector given a plane HKL? Now, it's quite straightforward to understand that if I have a plane HKL in parentheses, of course, then a vector with direction h, k, l in square brackets will be normal to the plane. And how do I know that? So suppose I draw another vector inside my plane of interest. This is the red vector here. Suppose its coordinates are u1, v1, w1. These are the indices of the new vector that I've drawn, and I propose that the vector that I need to find, which is uvw, is normal to u1, v1, w1. The two vectors will of course be normal when the dot product of these two directional vectors is going to be 0. So if u into u1 plus v into v1 plus w into w1 is 0, I would know that the two directions are normal to one another. The next step is to find the plane in which u1, v1, w1 lies. And we've already seen that in our previous class. So if I have, suppose the Miller indices of that plane are h, k, l in parentheses. So if I would like to find out a vector u1, v1, w1 that lies inside the plane, I would simply do the following. I would take u1, multiply it with h, v1, multiply it with k, w1, multiply it with l, and put this equal to 0. So I have equation number 1 and I have equation number 2 here. And by comparing these equations, one can immediately tell that the Miller indices are the following: h equals u, k equals v, and l equals w. Very straightforward. So what this means is the following. If I have a plane with Miller indices h, k, and l inside a crystal structure or a lattice, then the direction, the vector h, k, l with the same indices put in square brackets is going to be normal to the plane. So if I specify the Miller indices of the plane, I automatically know what the direction coordinate or the normal vector to that plane is. So I have a plane, suppose I have a plane, I draw a plane which is the 1, 1, 1 plane. What would be the normal vector? The normal vector would be 1, 1, 1 in square brackets. So this direction is going to be the normal to the plane. So instead of drawing planes, I can also draw directional vectors. But whenever we talk about vectors, we have two quantities at stake. We need to specify the magnitude of the vector as well as the direction of the vector. Now we know how to specify the direction of the vector. We choose a family of planes inside a crystal and specify the normal vector to all of those planes. Those planes, by the way, are all parallel to one another. So there's going to be one direction that specifies a family of planes. But this next thing that we would like to do is we would like to find out the magnitude of the normal vector. And this is where the concept of the reciprocal vector or the reciprocal lattice comes into play. And by the way, why are we doing all of this? Uh, we are doing all of this because we would like to understand diffraction. And this is the tool of choice for looking inside or peeping into crystals. And we can diffract with different kinds of particles or waves. We could diffract with electrons, with neutrons, and with X-rays. And we need an explanation of how do these particles or waves or fields interact with the crystalline structure, which is periodic, which has a high degree of symmetry perhaps. So we would like to use this concept of the reciprocal lattice in order to describe diffraction patterns. Just to give you a further motivation, suppose I have a single crystal, and I'll talk about single crystal and polycrystalline materials later on, but suppose I have a single crystal and I look at the atoms inside the crystal, they all lie in planes, on planes. So here I'm doing a cutaway of a crystal, and these black dots now represent atoms, real atoms, not just lattice points. And suppose that X-rays come in and a monochromatic collimated beam of X-rays comes in. So it's possible that it passes straight through and no reflection occurs, no scattering occurs. Now there is a particular angle between the planes that I've drawn and the incident X-rays. Let's call that angle theta. Now this is an empirical evidence. This is what really happens in an experiment. Now what I would like to do is I change the orientation of the X-ray beams. So there are two approaches for doing this. One approach is either changing the orientation of the X-ray beams or rotating the crystal itself. And the latter is more common. However, for simplicity, I'm just showing this in an equivalent fashion that I'm rotating the orientation of the X-ray beam. A new angle is formed between the planes and the X-ray beam. And still no reflection occurs. The X-rays pass straight through. Now what really happens inside a crystal is exactly what we are observing. However, in certain cases, if the relative angle between the X-ray beam and the plane of crystals, sorry, just matches the right angle, just this angle becomes the right angle. Immediately at that point, reflection occurs and a strong reflected beam is observed. So there are certain angles, these are not really angles of incidence, but grazing angles in a sense, because angles of incidence are defined differently. So this is the angle between the incident vector of the incoming X-rays and the plane of the reflecting atoms. These planes are just reflecting like mirrors and no reflection is observed. And all of a sudden, when the angle theta hits the right value, ping, reflection is observed. So reflection is only observed for certain values of theta. Now, how do we explain all of this? So if we get an X-ray diffraction pattern, uh, we could see peaks at different values of theta and no peaks elsewhere. So at precise values of theta, theta 1, theta 2, theta 3, do we observe diffraction peaks? So how do we explain all of this? That's why we're invoking this concept of the reciprocal lattice, because it facilitates an understanding of this quantization of space. Yes, Mariam.
Sir, the values of theta, are they material specific? As in, can we describe, can we identify a material looking at its peaks?
Exactly. So what we could do, so X-ray diffraction helps us identify the identity of atoms, the arrangement of atoms inside the crystal. So it helps us identify the space group of the material under investigation. And it also tells us the identity of those elements or atoms placed inside. That's why X-ray diffraction is an indispensable tool. It helps us tell the structure of the material. It's a characterization tool. All right, so now let's coming back to the concept of the reciprocal lattice. Let me change the color back again. Oh God. All right, so now we have a means of specifying the direction of the normal to a plane. So we have a means of identifying the plane. But let's look at a few concepts. Suppose I have plane, a plane inside a lattice or a crystal structure, and I have a family of planes.
Sir,
G.
sir, so the example you gave earlier about when we were using X-rays, so is it possible that X-rays they get reflected off one sheet, but then the reflected ray gets reflected back again through another sheet, so we never actually observe a beam coming out. It gets internally reflected.
Yes, it's very much, it's possible. You can have these cross effects,
So
but
then, how would we know that what material are we looking at if this is happening?
well, it doesn't really happen. So it's very unlikely that this happens, but it's possible. So you have waves coming off from different planes, and all of those waves interfere. And if you have a large number of planes, those you get a sizable reflection in a particular direction. Now, if you talk about cross effects, cross matrix effects, they do happen, and it is possible to investigate in a precise sense what diffraction pattern would result because of these cross effects. Okay. All right. So now
All
I'm
right,
drawing
sir.
a family of planes. The orientation of these planes is well defined. Now, in this family of planes, another important, so let's call this family of planes H, K, L, and now I'm going to put these brackets because there's a family of planes, or I can simply write H, K, L. Sorry, let's not confuse the discussion here. Let's simply write H, K, L for this family of planes in parentheses. Of course, I can define a normal vector, which let's call it D, H, K, L. And let's put an asterisk on top of this vector just for the time being and put a vector sign. We know the orientation of this vector because we know the orientation of the planes. But what is the length of this vector? All right, so what the concept of reciprocal lattice tells us is that one needs to know the spacing between these planes. Suppose the spacing between these planes is DHKL without the vector sign. That is the amount of spacing between these planes or the interplanar spacing. Now, the concept of reciprocal lattice is that this vector that I've drawn over here, this vector has a particular direction and it has a particular magnitude. And the magnitude of this vector is some constant divided by the interplanar spacing. So the interplanar spacing comes in the reciprocal position, comes in the inverse position as far as the length of the vector is concerned. And you need to put in a certain constant of proportionality at the top. So physicists and crystallographers disagree a little bit, but I would put the value 2 pi here, okay, in keeping with many physicists. Some textbooks would just put 1 here, okay. So I'm using this convention that the length of this vector, now I'm calling this vector a reciprocal vector for obvious reasons. It's like a blind man's walking stick. It's the blind man walks in a particular direction, but the stick is normal to the direction in which the blind person would like to walk. And the length of this vector is inversely proportional to the step size which the blind man takes. So this kind of vector is called a reciprocal vector. All right. Now,
सर
why
ये
is it G?
ब्लाइंड मैन वाली एनालॉजी दोबारा बता दें.
So in the blind man's analogy, so a blind man walks and the walking stick points in the direction along the direction of propagation normal to the surface of the person himself. So the stick points in the direction in which the person would like to walk. Okay. And suppose the length of the stick is variable and it's inversely proportional to the step size. Okay.
ठीक है.
Now let's advance this concept a bit forward. If I have the same family of planes, but now the planes are placed closer together, the same orientation, but now the interplanar spacing has decreased, diminished. The reciprocal lattice conferred by these planes is now longer because the interplanar spacing has decreased. So if the interplanar spacing is d, the reciprocal lattice has a length 2 pi over d, which is longer than the previous case. So now we know everything about planes through the reciprocal vectors. We can either choose to draw planes, keep on drawing planes and planes and planes inside a crystal, or we could just simply like to draw reciprocal vectors. Okay, and these reciprocal vectors are now part of what is called a reciprocal lattice, and that's what I'm going to describe in right now. Suppose I have a cubic lattice, and I simply talk about a primitive cubic lattice for the time being. Okay, and what I'm trying to do now, instead of x, y, and z, I specify the vectors as a, b, and c. And a, the length of a and the length of b and the length of c are all equal. Okay. Now, uh, this is a lattice. So, and the lattice points are on the vertices of this cube. And all of these lattice points are totally equivalent. There's no difference between one lattice point to the next because each lattice point has the same environment. That's how we define a lattice. This lattice exists in real space. And sometimes it's called a direct lattice. Now, when we look at a projection of this lattice from the top, we look down the z or the c axis. This is what we get. We have an a vector and we have a b vector. Okay, and here we have the lattice points. Now let's identify the planes inside this lattice. Now look at the unit cell. By the way, we haven't yet placed atoms inside this lattice, but still we have lattice points nevertheless. So let's talk about the planes for a minute. So lattice points exist on this plane, which is the same as this plane. And this plane is what are the Miller indices of this plane? Hey guys, Miller indices, please. Anyone?
010.
Incorrect. This is 100 because you move along the x direction, you make one crossing. You move along the y direction, you never cross a plane. So it's 100. All right. We can have this plane. This plane is the 010 plane. Okay. Now, in order to identify these planes, what we could do now is, now the 100 plane is identified by a vector. The c axis is coming out of the plane of the paper, by the way. So now I have a vector. Uh, so let's draw these vectors now. So I take an origin, some point, and I draw a vector which I'm showing in purple. This vector represents the 1, 0, 0 plane because it is normal to the 1, 0, 0 plane. Okay. And since this vector is also normal to the BC plane, let's call this vector A star and put a vector sign on top of it. Okay. And just by luck, the vector A star is also parallel to A. But that's because we're dealing with a cubic system. But the vector A star specifies the plane 1, 0, 0. So I can write A star is perpendicular to the 1, 0, 0 plane. Now I can draw another vector, which I'm now going to draw in red, which is normal to the 0, 1, 0 plane. And here it goes. And I give it the symbol B star because it is normal to the AC plane. So my B star is normal to the 0, 1, 0 plane. All right. And then if I were to talk about 3 dimensions, the C vector, lattice vector is coming out. And if I identify the base of this unit cell, what is the base? What are the Miller indices for the base?
001 जो C plane
That 0, 0, 1. So I can specify a vector that is coming out of the plane of the screen. Just in perspective, I draw it in this fashion, coming out. Okay. So I'm not going to draw the green vectors again because I'm going to concentrate right now on the uh, on the plane, on the basal plane. All right, so this is my third vector, C star, nevertheless. And this C star is normal to the 0, 0, 1 plane. And keep in mind, I'm talking about the cubic system here. So now I have a trio of vectors, A star, B star, and C star. These are normal to the planes inside a cubic unit cell, a primitive cubic unit cell. These vectors are called reciprocal vectors. And just as A, B, and C form a basis for the direct space, A star, B star, and C star form a basis for the reciprocal space. Okay, and if I go forward, I take this discussion a bit forward, I have the A star vector and the B star vector, and the length of both of these vectors is the same. What is the length of these vectors? If my direct cell, unit cell, has a cell dimension A and it's cubic, so each side has a length A, what would be the length of this vector? It's going to be 2 pi over A. And the length of the B vector is going to be the same because it's cubic, and it's going to be the same as the length of the C star vector. So now I've specified the reciprocal vectors as well as the length of these vectors. Okay. Now what I could do is the following. I could now do something really cheeky. I put a dot here, a point here, and a point at the end point of A star and a point at the end point of B star. Now this, instead of specifying the vector, I can specify the end point of the vector. That's good enough. So the end point of this vector now becomes a lattice point, but a point in the reciprocal space. Okay. And this point, in fact, represents a plane. The plane that this point represents is 1 0 0, and the plane that this point represents is 0 1 0. Just what we've done here. So this point represents this plane, and this point here represents this plane. And likewise, I can talk about other directions inside the lattice. So if I, if for example, I draw the cubic lattice in projection, the direct lattice, sorry, so the red is the direct lattice, cubic lattice in projection, A vector, B vector, and I can specify planes. For example, here is one plane. I've already done this by the way, so here is another set of planes. Okay. Now these planes are, so you start off at any point. These are the planes that are uh, on the edges of the unit cell. So now what I could do, I could draw normal to this plane. So I start off with an arbitrary position. I draw the normal to this plane. I draw a vector which I'm suppressing, and I draw the end point of this vector. So this point now represents the blue plane, which is 1 1 0 0. Then I draw a vector normal to the green plane, and I just suppress the drawing of the vector and just identify the locus of the end point. So this point represents 0 1 0. Likewise, I can have a plane of this kind, of this kind. This plane has a Miller indices 1 1 0, and I can specify the unit, the normal to this plane, and I just take this vector and start from the same origin. I will end up here. Okay, this point therefore represents the family of planes 1 1 0. If I were to draw planes that are halfway inside the unit cell, so if this were a by 2, then this family of planes, which are separated now by a by 2, they can also be represented by a vector. Now the vector happens to be in the same direction as the a star vector, but it's double the length because now the interplanar spacing is halved. So corresponding to this family of planes, I now have a point at 2 0 0. Okay, because this the length of the vector starting from this origin 0 0 0 has now doubled. So likewise, I can compose this entire lattice, which I'm showing in black points, on either direction. If I were to draw a plane of this kind, a family of planes of this kind, okay, now this family of planes, or each plane has Miller indices 1, 1 bar 0, and I can draw a unit normal to these planes, okay, like this. I just take this vector. Vectors can change their position. It's the length and the orientation of the vector that matters. So I just take this vector, place its tail at the origin, and this is where I would end up with. So this point is identified as 1 1 bar 0. This point would be identified as 0 1 bar 0. This point would be identified as 1 bar 0 0. This point would be identified as 1 bar 1 0. This point would be identified as 2 1 0. So now each point in this reciprocal space or reciprocal lattice in which the reciprocal space is the domain of the reciprocal lattice. It's where this reciprocal lattice lives. Each point in the reciprocal lattice represents a family of planes in the direct lattice. In the direct lattice. So this is the key idea. And why is the reciprocal lattice so important? We learned that most of the physical properties, the electronic properties, as well as diffraction patterns can be readily understood in the language of the reciprocal lattice. Now, if I were to do this in 3 dimensions, and I'm still talking about the cubic unit cell, I will have, so if I draw the reciprocal lattice in 3 dimensions, so I'm drawing a perspective view. So this is my reciprocal basis vector A star. This is my reciprocal basis vector B star. And then I have a reciprocal basis vector C star. So this entire set of points is lying in a plane. And these points represent the planes HK L equals 0. So this is called the HK0 net of points in the reciprocal space. But above this plane, there is going to be another set. So let's, for the sake of visual appeal, draw lines or grids between these points. Just for the visual appeal, okay? Now, I have a net above this, exactly above, of lattice points in the reciprocal space. Okay, so this is the HK1 net. So if I take my origin to be here, say, so this is my 0, 0, 0 plane. This would be my 1, 0, 0 plane. So I could use the plane synonymously with the point in the reciprocal space. Okay, so points in the reciprocal space stand for planes in the direct lattice. This point directly above will be 0, 0, 1 plane. This point here is 1, 1, 1. This point here is 1, 1, 0. This point here that I can draw is 1 bar, 1 bar, 1, and so on. So there are reciprocal vectors in the reciprocal space, and these reciprocal vectors end on points, and you form all the points in the reciprocal space, you get the reciprocal lattice. So a general point in the reciprocal space could be represented as H with the unit vector A star plus K with the unit vector B star plus L with the unit vector. So this is some general vector in the reciprocal space. So this is a reciprocal vector. In the direct space, we had the basis vectors A, lattice, which were the lattice vectors B and C. And you could specify the directions of the points in the direct space by some, say, M1 or UVW or something, anything that you like. These are integers. So this is a point in the direct space. I represent this by T, which stands for translation. So these are my direct vectors. Okay. So the concept and the thing about here, if you look at the size of a cube inside the reciprocal space, what's the size of the unit cell for a cube in the direct space? What's the volume?
सर रेसिप्रोकल स्पेस में
डायरेक्ट में क्या है और रेसिप्रोकल में क्या है?
डायरेक्ट में हमारा ए बी सी होगा और रेसिप्रोकल में हमारा ए स्टार बी स्टार सी स्टार
क्यूब की बात करें तो इन द डायरेक्ट इट्स ए क्यूब
और फिर
एंड
रेसिप्रोकल में ए स्टार क्यूब
in the reciprocal space it's 2 pi cube over a cube, because the length of each vector in the reciprocal space is 2 pi over a. Okay, you can't just say a star b star c star b because we're talking about cubic system here. It could be more complicated than that. So the volume, so bigger the size of the unit cell in the direct space, the smaller would it be inside the reciprocal space. Now if you consider an orthorhombic, so let's consider an orthorhombic unit cell in which all three sides are unequal, but the interaxial angles are, all three of them are 90. So you have a vector, b vector, and you have a c vector. Okay, now all three lengths are unequal. So this length is a, this length is b, and the height of the unit cell is c. And still we're talking about the primitive orthorhombic. So if I were to draw the reciprocal lattice for these points, I can also draw unit cells in the reciprocal space. So let me try doing that. So my A is, so this is going to be my A star, my B is going to be small, C is going to be the largest. So this is my reciprocal unit cell, the unit cell in the reciprocal space, in which this is my A star vector, this is my B star vector. My B star vector is normal to the AC plane. My A star vector is normal to the BC plane. And my C star vector is normal to the AB plane. So this is how I define these vectors in the orthorhombic, cubic, and the tetragonal unit cells. Okay. Now the lengths I've intentionally drawn them to be representative of the situation that we have over here. So A is a length, and this length is going to be, excuse me, this length is going to be 2 pi over A. B is large, so this length is 2 pi over B is going to be small. C is small, therefore this length is going to be large, 2 pi over C. All right, so this is a unit cell in the reciprocal space. All right, so any questions up to this point? So 1 minute of silence means really there are no questions. Okay, so now let me give you an example of a monoclinic direct lattice. So in a monoclinic direct lattice, you know that two angles are 90 degrees. Alpha and beta could be 90 degrees, and gamma could be different from 90 degrees, and all three lengths are unequal. So, so if I were to draw the projection on the AB plane, so this is a unit cell here. Okay, so this is my A vector, my B vector. Now keep in mind that the A vector is not orthogonal to the B vector. So this is something really important, and this angle here is gamma. Suppose my gamma for this case is greater than 90 degrees. Now I would like to draw the reciprocal vectors. I just identify the planes. This is my 1, 0, 0 plane. I identify the reciprocal vector normal to this, A star. Okay. And then next what I would do, something interesting is going to come up. I identify these planes. These are my 0, 1, 0 planes. I identify the vector that is normal to these planes. I use the same origin and draw this vector B star. Now the length of B star is inversely proportional to the spacing here, B, and the length of A star is inversely proportional to the spacing between the orange planes. Now this angle you can geometrically show is equal to the complement of gamma, gamma star. So gamma star is 180 minus gamma. Now the two reciprocal vectors, they are not normal to one another. Okay. But B star is always normal to the AC plane, and A star is always normal to the BC plane, and the C star is always normal to the AB plane. But A star is not necessarily normal to B star. So in the reciprocal space, these basis vectors need not be orthogonal with one another for generalized unit cells in the direct space. The so I can construct now the reciprocal. Let me use black here. I can construct the reciprocal space. Let me do this properly. This is a unit cell in the reciprocal space, and I can extend this. So this is 0, 0, 0 plane. This is 1, 0, 0. This is 0, 1, 0. This is 1, 1, 0. This would be 0, 1 bar 0. This would be uh, 1, 1 bar 0, and so on. So this is a net in the L equals 0. So this is an HK0 net in the reciprocal space. All right. So A star and B star and C star need not be mutually orthogonal to one another. Okay. So if I just want to show you something over here, if I look at A star vector and I also draw next to this, look at A vector and look at A star. So A vector turns out to be parallel to the A star vector. But that's not true for B and B star. B and B star are not parallel to one another. Okay. So here you can see B star is in this direction and B is like this. So they're not they are not normal to one another. They are not orthogonal to one another. Rather, there is a certain angle. So between them, let's call this angle phi. So if I were to take B and form its dot product with B star. So how do I form dot products? I take B. The length of the B vector is simply B. Okay, the interplanar spacing. So B is this thing here. Uh, B is this length. I've already identified B. This is B. And B star is what we have over here. And cosine of phi. All right. Now I replace B star, the magnitude of B star, with 2 pi over the interplanar spacing. That's what the length of the reciprocal vector is, cosine phi. Okay. Now, if you look at B cosine phi, so how do we, B cosine phi would be this particular distance from the origin. This is going to be B cosine phi, and this is equal to D. This is how far a plane is from the origin, and you always look at the normal. So if you want to find the distance of a plane from the origin, you drop a normal from the origin to the plane, and that is going to be B cosine of phi, because this angle here is phi. Okay, so if you do that, B cosine phi is D, so this turns out to be 2 pi. Okay, so if I were to take a unit vector in the direct space and find its dot product with the reciprocal vector, I will get 2 pi. B dotted with B star will also be 2 pi. C dotted with C star will also be 2 pi. Okay. And A dotted with B star. So if I look at A and I look at B star, there there could be some angle between them, but that's not what concerns me at the moment. So generally, what I would like to show you now is the following. So, so this approach of introducing the reciprocal lattice and the reciprocal vector is not very common. In textbooks, the kind of approach that you would find is the following. If I have direct lattice vectors A, B, and C, it corresponds to a reciprocal lattice with primitive unit cell vectors given as A star, B star, and C star, such that A star equals 2 pi B cross C divided by the volume of the direct unit cell. B star equals 2 pi C cross with A divided by V. C star equals 2 pi A cross with B divided by V, where V is the volume of the unit cell. So if I were to draw a parallelepiped which is representative of a primitive unit cell in the direct space A, B, and C, what's going to be the volume of this object? Anyway, so from basic geometry, we know that this volume is going to be A dotted with B cross C. So B cross C is normal to the So this is B cross C's. Sorry, B cross C is a vector normal to the AB plane. This thing here. And then you form the dot product of this B cross C with A, and these are not necessarily parallel to one another because of the shape of the unit cell, but you form the dot product, you get the total volume of the unit cell. If B, A, and C are all three of them are orthogonal, as it happens in the cubic, tetragonal, and the orthogonal unit cells, then this volume turns out to be ABC. So the direct volume is A dot B cross C. And this is what goes into the denominator of these expressions. So if I were to look at these expressions and I would form A dotted with A star, what would be my answer? My answer would simply be 2 pi. B dotted with B star would be 2 pi. C dotted with C star would also be 2 pi. Okay. What would A uh, what would be A dotted with B star look like? Anyone with the answer? What would A dotted with B star look like? Come on, guys, this is easy. This is B star. If I form the dot product of A with B star, what would the answer be? Hmm? What is the answer for this vector expression? Come on. What is the dot product of a vector with a cross product of the same vector with anything else?
0.
Zero. Come on, इसमें क्या मुश्किल है भाई? This is going to be zero. So I take any unit vector in the direct space, form its dot product with any other different kind of vector in the reciprocal space. So A dot B star, A dot C star, B dot C star, and so on. The answer will be zero. And the reason for this is that the reciprocal unit vectors are normal to the planes with the other two variables. Okay. So, so this is the overall concept of the reciprocal lattice. So any questions?
सर इसमें जो कि हमारे पास रेसिप्रोकल करके जो एंगल चेंज हुआ था बी और बी स्टार का, अगर वो एक दो दोबारा बताते हैं तो प्लीज।
देखें, here this is the direction of B of the B vector, right? Left to right.
यस।
Okay. Now the plane 0, 1, 0 has an orientation shown here in purple. Okay.
यस यस ठीक है।
Now the vector that is normal to this plane is going to be B star, and this is the vector. Of course, B is not the same as B star. They are not parallel to one another. They are coplanar, but they have a mutual angle between them. Okay, so this is B star, this is B. B and B star, by the way, live in different spaces. B lives in the direct space and B star lives in the reciprocal space. But they are not parallel to one another. Okay, so that's the concept that I wanted to bring home.
All right, sir. ठीक है. Thank you.
or unit cells in which the mutual interaxial, the unit cell lengths or vectors are orthogonal, which is cubic, tetrahedral, and orthorhombic. Only for those particular cases, A star will be parallel to A, B star will be parallel to B, and C star will be parallel to C. All right. So this is the overall concept. Now, what I would now like to finish off this lecture with is the following. So now, these are definitions that we would like to remember, and they follow from the discussion, the intuitive or the graphical discussion of building up the reciprocal lattice that we've already seen. Okay, so it's we have 14 kinds of Bravais lattices, don't we? So each one of those will have a different kind of reciprocal unit cell, and it's very important to understand this. Now, what I would like to do now is form the reciprocal lattice for a body-centered cubic cell. So I have a body-centered cubic unit cell, of course, in the direct space. So let me draw this. Excuse me for a minute, please. All right, so I'm going to put points here representing the body-centered lattice, points at the vertices. And a point at the body center. Now, this is not a primitive unit cell. Why is this not a primitive unit cell?
उसके सेंटर में भी एक एटॉमिक कंट्रीब्यूशन है.
Right, because it has 2 points per unit cell. A primitive unit cell has 1 point per unit cell. So it's body centered. All right, so now what we would like to do, if you look at this unit cell, there are planes of points, and you can draw multiple planes of points. But you need to take into account this position at the center of the body of the unit cell. You can have atoms here, you can have motifs here. So what you would like to do, it's always possible to draw a primitive unit cell, even though the lattice type is body-centered, face-centered, or base-centered. For example, in this case, if I were to draw a primitive unit cell, which of course will no longer be cubic, it's very much possible to do that. So if I were to take a vector here, and I were to take a vector here, and I were to take a vector here. So let me use different colors for these vectors. I'm still in the direct space, by the way. So I draw a vector here. I draw a vector here. And I draw a vector here. I can identify these vectors as A, B, and C. Okay. Now with these A, B, and C, I can draw primitive unit cells for this otherwise body-centered cubic lattice. The primitive unit cells, no doubt, will have a lower symmetry than the cubic unit cell, but still these will be unit cells nevertheless. So in order to invoke this concept, suppose I have a planar lattice, and at the center of each base I put point, another point. So I have points at the vertices. Now this is a base centered planar lattice or a face centered planar lattice. I can always draw this primitive unit cell of half the size of the original, but still it's going to be a unit cell because these unit cells are going to fill up all of space. So I can always draw primitive unit cells if apparently my lattice type has a body centered or a face centered or a base centered disposition. So I started off with this body centered cubic unit cell and chose a primitive unit cell basis A, B, and C. Now my vectors A. Now, can we specify the vector A? I can use the fractional coordinates to do that. So my base will be at half, half, half. This point is going to be 1, 1, 0. This point here is going to be 0, 1, 1. These are fractional coordinates that I'm writing here. And this point is 1, 0, 1. So what is my vector A going to look like? What is my vector A in terms of the fractional coordinates? How do I know? I take the final point minus the initial point. That's what I would like to do. So the length of this vector. So what I could do, I would take 1 minus half is 1 half. 1 minus half is 1 half, and 0 minus half is minus half. So I get 1 half, 1, 1, minus 1. So this is my, now since I'm writing vectors, I can use square brackets. Okay, so this is my vector A. Likewise, I can define vector B. So my vector B is going to be 0 minus half is minus half, 1 minus half is half, 1 minus half is half. And my vector C likewise is going to be, so I just write down the result, is going to be 1 half minus half, 1 half. So these are my vectors A, B, and C. All of them as fractions of A, of the length A. Now I can use this prescription here to find out the reciprocal vectors A star, B star, and C star. And then what you could prove is that if I were to write down the vectors A star, B star, and C star, they would form a face-centered unit cell. Now, is can you do this on your own? Can you do the algebra on your own? Can you find out A star, B star, and C star?
Yes, sir.
Right. So if I were to find out A star, B star, and C star, my final results would be the following. So by the way, so these are in units of A, so I can put a unit of A here. if I do absolute units, because I want to do absolute units when I'm dealing with the reciprocal space. So A star turns out to be 2 pi over A 110. P star turns out to be 2 pi over, excuse me, just a minute, just my, okay, 2 pi over A 011. C star is 2 pi over A 101. Now, by looking at these reciprocal unit vectors, would it be possible for you to draw a unit cell? These are primitive reciprocal lattice vectors. So what will the unit cell look like in the reciprocal space? So here is my origin 0, 0, 0. Now I'm talking about planes because I'm identifying the points in the reciprocal space by planes. So my origin is 0, 0, 0. My first reciprocal vector, unit vector A star, look at its values 1, 1, 0. So this would lie, make a point. The reciprocal vector will be, can be drawn by this ending, making a point here. This is my A star vector. My B star vector will be, so okay, let me also draw the, right on the unit cell. So this point really is, excuse me, 1, 1, 0. Explain that in a minute. So B star is going to be 0, 1, 1. It's going to produce a point. So my screen, sorry, is again giving me trouble. Can you give me a second? I just want to change this the battery in my pen. Just a minute, please. In the meantime, would you like to ask something?
सर ये जो आपने अभी ब्लैक में क्यूब ड्रॉ किया हुआ है तो इसकी जो लेंथ्स हैं यूनिट लेंथ तो ये कितनी है जिसकी वजह से हमें पता लग रहा है कि 2 पाई ओवर ए से वो यहाँ पर पॉइंट आएगा सेंटर में करके कहीं पे।
मैं बताता हूँ अभी, एक मिनट बताता हूँ. So let's first finish this drawing this. So B star is, gives me a point z, x is 0, y is 1 here at the center of the back face, this face, right? So this point is, represents the plane 0, 1, 1. The third point, C star, and this is my B star. The third reciprocal lattice is C star. This is at 1, 0, 1. So it gives me a point at the center of this face. This is C star. And this point has, represents the plane 1, 0, 1. So now what you observe is the following. You have a point in the reciprocal space at the origin and one point at each of the three faces. So if there's a point here, there's going to be a point here, there's a point here, there's going to be a point here, and there's a point here, there's going to be a point here. And this is nothing but a face-centered unit cell. So if I started off with a body-centered unit cell in the direct space, In the reciprocal space, I get a unit cell which is face centered. And the points on the vertices and the centers or the faces of this reciprocal unit cell correspond to planes. Now let me draw this unit cell again. And I'll answer, probably Bilal asked this question or Heather asked this question. So I'm now in the living in the reciprocal space, and I'm drawing a unit cell in the reciprocal space, and the unit cell in the reciprocal space is body centered. Oh, sorry, is face centered. So I have points here, and I have points at the front and back faces, and points at the left and the right faces, and points at the top and the bottom. So these solid lines that I've drawn, they are just for visual clarity. So this is my 0, 0, 0 plane. This is my 1, 1, 0 plane. This is going to be my 2, 0, 0 plane. This is going to be my 2, 1, 0. This is going to be 0, 2, 0. Here I will have, so let's first finish off the edges. This is going to be 2, 2, 2. This is going to be 0, 2, 2. Here I will have, sorry, this is going to be 0, 0, 2, 2, whereas this here is going to be 2, 0, 2. 0, 2, 2, and this point is going to be 0, 0, 2. Here I will have 2, 0, 2. This point here is 1, 0, 1. This point here is 1, 2, 1. Here I have 2, 1, 1, and here I will have 0, 1, 1. And you could look at your body centered direct lattice, and draw planes inside this body centered. For example, this point here, 2, 0, 0, corresponds to a plane that I would like to draw right now. So I draw a plane in the middle of this body center here. This is my 2, 0, 0 plane. And in the reciprocal space, this is represented by the point here. Okay. Right. So this is how, and this is further away, because if I, okay, so if I were to draw another plane, for example, this plane here, this plane here is 0, 0, 2. That goes here in the reciprocal space. So the closer the plane is to the origin, so if I were to draw another plane, so let's be tongue in cheek, let's draw another plane here. This plane is 0, 0, 4. In the reciprocal space, this point will go further up. It will go up here. This will be 0, 0, 4 will go up here, sorry, vertically upwards here. Okay, so this will be 0, 0, 4 point. So planes that are closer to the origin in the direct space, they will be further out from the origin in the reciprocal space. And the key point here is that if I took a body centered unit cell in the direct space, in the reciprocal space, the unit cell will be face-centered. And in homework number 3, I'll give a problem that if you start off with a face-centered unit cell in the direct space, in the reciprocal space, its unit cell will be body-centered. Now, one question I would like to ask you, because I talk too much and you don't talk enough. Probably it's because of this online scenario. The question that I would like to ask is the following. By all of this discussion, do you find any, of course, the resemblances between the direct and the reciprocal lattice are clear. Both of them are lattices. They represent points in space. And we know that in the reciprocal space, each point represents a plane. It stands for a plane in the direct space. But are there any other differences which stand out as far as the direct and the reciprocal lattices are concerned? Any conceptual differences that you find? So I give you 1 minute to think about this, please. कुछ कह दे, कुछ भी कह दे, कोई फर्क नजर आ रहा है आपको?
लेंस जो हैं वो जहाँ पे छोटी थी वो जो है वो उसी हिसाब से वो इलोंगेट हो जाती हैं रेसिप्रोकल स्पेस में।
ठीक है, लेकिन ये तो सिर्फ एक इन्फ्लेशन और डायलेशन का मसला है कि in the reciprocal space, so you have a smaller unit cell in the direct space. In the reciprocal, it gets larger. So this is just a matter of scale. The key difference that I find very interesting, and I would like to highlight this, is that in the direct lattice, so I draw a unit cell here. Be it face centered, body centered, let's draw a face centered unit cell, orthorhombic. All points are the same because you perch yourself on any point inside the direct lattice, you will see the same environment. So there is no uniqueness about any point whatsoever. Every point is just the same. And there is no unique origin. You can choose any origin that you like if you would like to identify the fractional coordinates of the different points. However, this is not the case in the reciprocal space. In the reciprocal space, what we've done in all the examples that we've seen is that we've earmarked, identified each point with a distinct plane. And the choice of the origin is also important. So each point in the reciprocal lattice, even though it has the same properties as the same symmetry properties as the direct lattice, in fact, there are point groups for the reciprocal lattice, etc. as well. It's proper lattice. It will have those 14 Bravais lattices as well. It is a lattice in the mathematical sense, but each point in the reciprocal lattice stands for a different plane. So if I look at the point 0, 1, 1, 0, and I look at the point 2, 1, 0, these points, since they are in the points in a reciprocal lattice, they represent different planes, distinct planes. So each point has a character of its own. And we learn in diffraction why this idea is really important. So it seems at the moment that the idea of the reciprocal lattice is very abstract and it's a mere fantasy of our imagination and it's of no use. But once you get the hang of it, once you understand the insights which are presented by the reciprocal lattice, you always want to think about diffraction in terms of the reciprocal space. You always want to think about the electronic properties of graphene, two-dimensional materials in the reciprocal space, which by the way is also called the K space or the momentum space. So if you are immersed into the field of condensed matter physics, you start thinking about the reciprocal space and you hardly think about the direct space unless you So if you want to present to the world what the structure looks like, you present it in the direct space. Where are the atoms geometrically arranged inside the unit cell? But you look at the diffraction patterns and you start thinking in the K space or the reciprocal space. So that's why this concept is really important, and not many students of solid state physics understand the vital importance of the idea of the reciprocal space. And the next couple of lectures, I'll bring home the idea of the reciprocal space. And one key idea that I would like to give is, and I'll just stop here, and it's the golden statement: the reciprocal lattice is the Fourier transform of the direct lattice. So I'll explain what this means in the next couple of lectures, and we'll hopefully finish our discussion with diffraction and the reciprocal space in one more week. So I'll stop here. Any questions?
Sir, when we're talking about the reciprocal space, does the symmetry always increase? Like we just saw that the body centered became a face centered.
So you can't say that the symmetry not necessarily increases. So a primitive remains primitive. But remember that when we a body centered you took a body centered direct lattice, you got a face centered reciprocal lattice. There are more points here. There are now 4 points in the reciprocal space, so more directions are available for the diffracted rays, but it's not necessary that the symmetry always goes up. It can remain the same as well.
Okay,
So
thank
a
you.
primitive unit cell remains primitive. Okay.
Excuse me, sir.
So I've scanned the remainder of the book as well. So I'll share the remaining chapters in the book, patterns and crystals, as well. So some of these ideas you can find over there. But mostly this material is gathered from different sources, and it's pretty much quite a non-standard way of teaching the subject.
सर अगर आपके पास
All
ऑफिस
right.
आवर्स में आना
Yeah.
हो तो आप अपने पुराने फिजिक्स फिट ऑफिस में होंगे या डीन ऑफिस में होंगे?
Mostly I'm in the physics office.
ऑलराइट सर, ठीक है, थैंक यू।